and they'll remain there stable. But we took this vesicles dispersion and we added another polymer, polyethylene oxide, which is soluble in water, but it's going to disrupt an otherwise stable dispersion of the vesicles. And we wanted to see what happened when we did that, really. So this is just a series of what started off as dispersions of vesicles. So 0.25% and 0.5%, so they're all the same, just different concentrations of the vesicles in solution. And then across, we're adding more and more of the PEO polymer into the solution. And this is how they started. So we've just got a cloudy dispersion of the vesicles in solution. So at this point, we've just added the PEO to the solution. And took a series of photographs over a 48-hour period and just left it sitting there. And so you can see we completely disrupted what was usually stable for months and months on end. In a matter of a day, the whole system had crashed out, forming these lumps of gel in solution. And you notice at the, this one moves faster, the lower concentration of PEO added, the solutions sink in solution, whereas they float when we add too much PEO. But either way, we're disrupting it and crashing it out, causing something to happen, but it's clearly there's a difference there's a critical point of how much PEO you can add, and we're getting two different things going on.
Was there a question?
Oh yeah.
Sorry.
Okay.
Wait, what was PO? Sorry.
It's another polymer chain. It's polyethylene oxide. It's soluble in water, but it's going to change the properties of it. And what it does into this system, I'll actually explain in a couple of slides. So that might answer the question, but please shout if it don't. And so we took each of these samples and we freeze dried them. So you freeze them and take off the water, you maintain the structure that was left behind. As long as you freeze it fast enough that ice crystals don't fall in solution, but they're going to disrupt your structure and end up with all sorts. But the gels that we created that floated, where the vesicles had aggregated together, it's aggregating into big lumps essentially in solution. These are aggregated together because the solution was dry. These were floating around, dispersed normally, and then under drying, these have aggregated into big aggregates. But these singular balls are the vesicles that have aggregated together. To give you an idea of the scale, so these are 500, these are going to be probably 1,500 nanometers. We started off with vesicles that are about 200 nanometers in size. So if you think of a millimeter on your ruler, unless you all work in inches, which could be a problem, you divided that into 1,000 sections. One of those sections is a micrometer. And if you divided that into another 1,000 sections, one of those sections is going to be a nanometer. So that's the kind of unimaginable scale that we're working at here. And then looking at the solutions that sank in solution, so less PEO added to the system. What we saw was large interconnected networks together. And these are all micrographs taken on a scanning electron microscope. Using an electron microscope, yes.
What does the UM stand for? Two.
Oh yeah, sorry. So that's micrometers,
Oh, okay.
and then the NM would be nanometers.
Okay.
So these are a series of images, like zooming in on the same part.
Do you know why when you add a higher concentration of PEO, the gel floats and slower?
Yeah, so when in in the next slide. So taking these, so we wanted clearly two different things were happening. We're getting aggregation of the vesicles in the system, but in two different ways. And so looking at the lower PEA concentration is where we're forming this large interconnected network of gels. What was happening was the added PEA polymer was actually sticking to the surface of the vesicles. PEA is a very strange polymer. It is water soluble, but it kind of has its partially insoluble sections, and so when it sees the surface between the water and the insoluble block, it very gently sticks to the surface and adheres to that. And with the long chains, it then becomes looped around multiple vesicles in the solution, causing them to aggregate together. And when they come together, then they're fusing into these long network structures that we're seeing here. And that was what was happening with the low added PEA concentrations. At high PEA concentrations, you get an effect that overrides this and is much faster. I haven't really got the slide to properly explain that one. So these dispersions of vesicles are quite stable because this shell layer is so swollen with solvent that it's effectively like a barrier between any other vesicle that might come near it. And so if they do come near, this bulk of water that surrounds them is carried around and they can't come together. But if you add big polymer chains to a solution, then what you induce is a collapse in. So, can I draw on board?
There's a chalk.
Right. Sorry if this doesn't show up. Sorry. So you have what would usually be your vesicles floating around in solution, which is quite stable. But then you throw in, say, these big polymer chains floating around in solution. And what happens when, say, these vesicles come too close together? This polymer chain can't fit between the two here. So what you have is a high concentration of polymer around your vesicles, but no polymer within the vesicles. And so it's called osmotic pressure creates a movement of water out of this space, which in effect pushes the vesicles together, and which is what caused the mass aggregation before. It's a bit osmotic pressure in the same way as if you drank a cupful of salt, you'd be severely dehydrated because the water would then rush into your stomach because there's a high concentration of salt in the stomach relative to the rest of your body. So that's why we get the movement of water, because it wants to balance out that concentration difference.